There's something you trust your life with every single day, but probably never even think about: welding. And no, we're not just talking about some simple task in a workshop. We're about to dive into the deep, incredibly complex, and sometimes really violent science that, quite literally, holds our modern world together. Just think about it for a second. The airplanes we fly in, the bridges we cross, the power plants that light up our cities, all of them depend on joining these massive chunks of metal together. And that connection point, it's often a seam no wider than a few millimeters. An entire skyscraper, a whole ship, is trusting its integrity to these tiny fused lines. So that really begs the question, doesn't it? How can we be so sure that these microscopic connections will hold up against some of the most incredible forces imaginable? Well, the answer isn't just about good craftsmanship. It's about mastering a whole universe of physics happening at a scale that's almost impossible to see. Okay, so to really understand a weld, we have to start by zooming in, way in to the very moment it's created, the weld pool. And listen, this isn't some gentle little puddle of liquid metal. It's a tiny, raging cauldron of extreme physics. The weld pool is the absolute heart of the whole process. It's that one localized spot where the metal melts to form the joint. But yeah, calling it a pool is honestly a huge understatement. For that brief moment it exists, it's one of the most extreme environments you can create outside of a specialized lab. Inside that tiny drop, the physics are just wild. First off, the temperature right at the center can actually go past the metal's boiling point. That creates this high-pressure vapor that literally blasts away from the surface. This causes incredibly turbulent, chaotic flows within the liquid. And here's the crazy part. All of this intense evaporation actually creates a massive cooling effect right on the surface, making the whole system just unbelievably complex to predict. I love this analogy: a chaotic ocean in a teaspoon. It's the perfect way to picture it. All of this chaos, the boiling, the pressure, the flow, it all has to be controlled perfectly. Because what happens in the split second this tiny ocean freezes, well, that determines everything. So as that molten pool cools, and we're talking a matter of seconds here, the atoms inside have to find their new homes. They rearrange themselves into crystal structures, and the specific pattern they form becomes the blueprint for the weld's final strength, or its ultimate weakness. This process is called a phase transformation. It's a fancy way of saying the metal is literally changing its fundamental atomic structure. It's kind of like having a box of Legos that you could build into a solid, strong cube or a fragile, brittle tower. It all just depends on how you stack them as they cool down. So how do these atoms actually rearrange? Well, there are pretty much two main ways it can go down. A reconstructive transformation is slow, it's methodical. You have individual atoms moving around, almost like you're rebuilding a wall brick by brick. But a displacive transformation is completely different. It's a sudden, coordinated shift. A whole group of atoms shears into a new position all at once. Think of it like shuffling a deck of cards. This process is incredibly fast and creates these very different plate-like structures. And check this out. The speed of that cooling changes everything. In the molten pool, the steel starts out as something called austenite. If you cool it slowly, you get that gentle brick-by-brick change, and that forms a soft structure called ferrite. But if you cool it faster, you force that sudden card shuffle transformation. A fast cool gives you strong bainite. An instant cool, that traps the atoms in a super strange structure called martensite, which is incredibly hard, but also really brittle. So, you see, by precisely controlling that cooling rate, engineers can literally choose the final structure they want to create. But even when a weld looks absolutely perfect, there's a hidden danger lurking inside. You could call it a ghost in the metal. All right, so the weld's made, it's cooled down, it's solid. You might think the job is done, but the most dangerous part of the process is often what gets left behind, trapped inside the steel itself. Here's how this ghost gets trapped. When those new crystals form, they don't just have a different atomic pattern, they physically take up a different amount of space, a different shape and volume. But the metal all around the weld is already cold and solid. It fights back against this change. This conflict, this pushing and pulling at the atomic level, traps a huge amount of energy right inside the weld. We call it residual stress, and it's like a tightly coiled spring, just waiting for a chance to release. And you gotta understand that tiny atomic shift creates this very real physical stress on the part. The finished weld might look perfectly straight, but internally it's just full of tension, constantly trying to pull itself apart from the inside. This is the ghost that can cause unexpected cracks and failures, sometimes long after the job is supposed to be done. It all boils down to this really bizarre phenomenon called transformation plasticity. See, for that brief moment while the crystals are shifting, the metal becomes weirdly soft and malleable, and this allows those massive stresses to get locked in way more easily than you'd think. And that hidden behavior is what makes residual stress such a critical and dangerous problem to solve.
Okay, so let's recap. We've got a violent, chaotic weld pool, atoms rearranging at lightning speed, and these invisible stresses getting trapped inside the final product. How on earth do engineers control all of this? Well, they do it by building the weld in a computer first.
The answer is pretty amazing: computational modeling. Before they ever strike an arc of electricity, engineers create what's called a digital twin of the weld. They build a complete simulation that accounts for all of this insane physics, which lets them predict and control the final outcome with incredible precision.
And what these simulations can do is, well, it's just staggering. We're talking about predicting everything, from the turbulent fluid flow in that chaotic molten pool to exactly which crystal structures are going to form as it cools. And most importantly, they can predict the final distribution of those hidden residual stresses, telling engineers if a weld is safe or if it's a failure just waiting to happen. And this is what it actually looks like to an engineer. This isn't just some cartoon, it's a super sophisticated mathematical model showing the temperature gradients in and around a weld. They can tweak every single variable, the speed, the power, the material, and see the results instantly, designing the perfect, safest weld without wasting a single piece of metal. This is a complete paradigm shift in engineering. Instead of the old reactive, test it and see if it breaks model, it's a proactive, predict and design approach. By simulating everything first, engineers can dramatically boost reliability while slashing development time and material waste. It's an absolute game changer. So if there's one thing you should take away from all this, it's that the safety of the world around us really depends on mastering this invisible world of atoms. By understanding and modeling the entire life of a weld, from that chaotic molten pool to the final arrangement of its crystals, we can build structures that we can truly, deeply trust. Which kind of makes you wonder, right? What other seemingly simple things in our daily lives, from the glass in our phones to the rubber in our tires, are hiding a similar universe of breathtakingly complex science? Thanks so much for joining me.